everybody. In the interest of time, I think we will start. It's so nice to see so many of you here. My name is Morten Breivik. I'm the head of the Department of Engineering Cybernetics here at NTNU. Today we have the pleasure of having a very distinguished guest here at NTNU, Professor Karl Johan Åström. He was born in Östersund, Sweden. He received his master's degree in engineering physics in 1957, and he got a PhD in automatic control and mathematics in 1960 from the Royal Institute of Technology in Stockholm. He has worked at IBM Nordic Laboratory on computerized process control. He has also led efforts in computer control of the paper manufacturing industry. In 1965, he was named the chair of the newly founded Department of Automatic Control at Lund University in Sweden. And he has, in the period from 1965 to 2002, been chair of this department, where he is now a senior professor. He has also been a distinguished visiting professor at the University of California at Santa Barbara in the US. He is a fellow of the IEEE. He is also a member of the Royal Swedish Academy of Sciences. He has gotten a heap of different prizes and medals. I won't go through all of them, but one of them is the IEEE Medal of Honor in 1993 for his fundamental contribution to theory and applications of adaptive control theory. Åström has written at least 5 books that I know about. According to Sigurd here, who is his host for the rest of this day, his most important prize or award is the Nordic Process Control Award. According to us, his most important award is to be an honorary knight of the Order of the Golden Feedback Loop. That he got in 2004, and there is this symbol of it. He has a good, he's cited over 80,000 times, and he has an age index of 92, which is incredible. So we are very excited, Karl, to hear what you have to say on this exciting topic, fascinating history and success of feedback control. So please, Karl.
Thank you very much. It's a real pleasure to be here in Trondheim. It's so close to my hometown. And I've been here many times, particularly during the Balkan era. So I'm always envious about the strong institute you had here. And I started in Lund in '65. We've been building up, but we have a long way to go until we come to the size of the Cybernetics Institute you have here. So it's really a pleasure to be here. I should also thank Sigurd Skogestad for creating this title. I had a much more modest title here before, but Sigurd has a way with words, so I will thank you for that. So I'm going to talk about control. And it's a young field, compared to physics and chemistry and things like this. We are just beginning. And if you look here, that there are all examples of feedback system from bad times. But control really came across in connection with modern technology. When we got aircrafts, when you got electric power, when you got all process automation and things. There was always a need to keep the processes well in control. So around 1940, it became a separate discipline. It has developed very, very rapidly. And a couple of reasons for that. It's the first systems discipline, and it cuts practically across all engineering subjects. So in my mind, all engineers should study control. And I know that here in Norway you do this. We are not quite as successful yet in Sweden. For example, civil engineers don't study it. And that's why climate controls are so bad. There was a lot of stuff written around the turn of the century about control, and here are some of them. IEEE has published a document that's accessible from the web that's called The Impact of Control Technology. Here's a book that I was part of editing this together with Richard Murray, Control in Information-Rich World. And also the American Engineering Society, they gave out a book telling what the engineer was 2020. And 2020 is real soon now. They made another book called Educating the Engineer 2020. So I will give a couple of quotes for that and see how far we have come. I should probably get closer. I'll do it the real way. A long time ago, I wrote a paper called the hidden technology. And I was very pleased when there was an IFA Congress in Barcelona when they used this as a title for the Congress. And I call it the hidden technology for the reason that it's widely used, it's tremendously successful, and it's seldom talked about, except when there's a disaster. And now you have to look carefully here. If I can activate this one here. Yes, I can. This is from Swedish television. They were making a program about pilots, hero pilots, test pilots. And here he is coming in for landing. And it oscillates. This is live on Swedish television, showing, you know, how great pilots they have. Incidentally, what they've done here, they took one of the test pilots who was called hot on the stick. Here he just broke his arm. It's a strange picture. It's the Royal Insurance Building in Montreal. And it was one of the most beautiful buildings in Montreal, but it collapsed because it was on the same ground as you have here, and they have put, you know, lots of wood down there, and the wood broke. So it's, I put this up because it's important to have a solid foundation. And that's always been a hallmark of control. You know, sometimes we have complained of using a little bit too much mathematics, but that's really what gives us the sound foundation. So I'm going to skip this and jump directly to a brief history here. I said before that control is a very young field. And it started off when you use control in the different industries. So people found out that feedback was really useful. When you were generating electric power, you wanted to have 50 hertz in Europe and 60 in the US. So you wanted to have them rotating at constant speed. In process control, you wanted to keep temperatures, pressures, and concentration constant. In vehicle, you wanted to control vehicles. And in communication. And so it developed in all these areas, in particular in communications. You know, you had old telephones, you just had a wire and a microphone and a speaker. When you get long wires, you needed amplification. So there was a need to build electronic amplifiers that were extremely reliable and linear, based on very bad component, the voltage tube, the electronic tube. Which is non-linear and it's varying. So how can you make good components out of bad systems? So this happened here. And then Servomechanism Theory came around the, was essentially stimulated by the war effort. Many governments realized that engineering can play a major part in the war. So in many countries they gathered engineers and scientists in groups. And one of the most successful ones were in the United States, the radiation laboratory, where they developed radar. And in connection with this, the Servomechanism Theory came around. And these had tremendous consequences. Control spread like wildfire all across the world. So you get courses in control that were spreading practically over all countries. And then I think any field would be quite successful with it. But then we had what I call a second phase. That was driven by two things. One was a space race. You know, the Russians and the Americans were trying to put rockets and satellites up in the air. And that required a very large research effort. And secondly, we got computers. And we got computers to try to control industrial processes and many other things. So that gave us the second phase. Another feeling right now, we may actually be entering a third phase. Is there some evidence for this? Well, let's look at the publications. Here is a logarithmic scale, you see time, and here you see publications. Say up to 1940, there were about 100 publications in control. Not very much, hardly noticeable. Then we move up here when control, you see here there's a sort of bump. That's the war years, or what's coming after. And here you see we get a significant bump. And notice the scale here is logarithmic. So up here we had about 1,000 publications around. And then was a steady growth. And what's here? This is the second phase, when the space race and the computers, and then it started to grow steadily on here. So what I did, I went to Scopus, I Googled all papers that had in the title, abstract, or in the keywords, they had control, or feedback control. And that's how I got the numbers. So let's look a little bit at the field. So here's power generation. You wanted to generate, to have generated the run at constant speed. And the solution was a turbine controller. And whenever you close a feedback loop, you run into stability problems. So they needed a stability theory. There were really two sources. One was Stodola, who was a Swiss engineer, and he went to one of his friends in the mathematics department called Routh Hurwitz, and then they developed a stability criterion. And in England, Maxwell was working on this, and Routh made a stability criterion. You know, if you have a linear equation, stability is essentially finding out if the roots are in the right or left half plane, and you got the Routh-Hurwitz criterion. And then there was another, in Russia, there was an engineer called Vishnegradsky, who really made a very nice analysis of the steam engine. Maxwell had also done this, but Vishnegradsky was much more engineering oriented. And then of course we had Lyapunov, who published his thesis on stability, totally different approach for stability, looking at energy and things like this. And then also, we had the first textbook of control, as far as I know, written by a German called Tolle, and dealing with the power engineering problem. So here, you know, this is some of the heroes. This is Horowitz. This is Vishnegradsky. He had the Order of Lenin sitting there, and that's Lyapunov. That's Routh, incidentally. And out of this, we got, for example, the centrifugal governor. Then we take something that's close to here, what you do here in Sigurd Skogestad department, process control. There was a need to keep pressure, temperature, and concentration constant, and the solution was the PID controller. The side effect was an industrial standard for communication. And this standard consists of a tube, where you specified the dimensions of it, and also specified it should be between 3 and 15 psi. So that's one of the first communication standards. And because of the standard, you know, you could separate the controllers and the sensors, and you can build up systems. And then we got the famous rule for tuning PID controller by Ziegler-Nichols, 1942. So we owe a lot to process control, and of course this is still a very active field. And then we have something very interesting, flight control. You know, in the beginning of the previous century, many people were trying to fly. And most people who tried, they made stable airplanes. They got the plane up in the air, and then it fell stably into ground when you hit a bump in the air. But what the Wright brothers did, they made an unstable aeroplane. So it was unstable but maneuverable. And that was the key to their success. And they were actually, they ran a bicycle shop, the Wright brothers. So they had a very good feel for dynamics. So that was why they succeeded. And then as a result, of course, when you have to sit there and stabilize the aeroplane manually all the time, it's kind of tedious. So very early on, you get an autopilot. This is a picture from 1947. Up here is Sperry's son is sitting there, and look, he's stretching up, saying, look, no hands. And then the mechanic here is walking on the wing to put on a perturbation. So they were flying over Le Bourget airfield, and then the pilot steps down, they turn around, they flew back, and they got the prize for the most stable aeroplane. So here are the Wright brothers, and here's a picture of Sperry. And then, of course, airplane changed. So nowadays, most airplanes are stable, but there are still advantages in making unstable airplane. Like the accident I showed you, this is a Saab airplane that's unstable in certain flight conditions, namely takeoff and landing. And what you gain instead is that you're gaining maneuverability. So by designing a system that's intentionally unstable, you often get much better maneuverability, but then you are faced to make a control system to stabilize this. Then we move over to another field, telecommunications. And the problem was, as I said before, to communicate over long distances. And the key problem was to make a stable amplifier. And that was solved by making the feedback amplifier. So here I show a sort of simplified picture of this. And if you look at the input and the output relations here, you see the bad thing is this amplifier, because it's non-linear in its changes. But by rearranging this feedback loop, you get this relation between the input and the output. And look here, if K is large, K is very large, you see, then these two terms dominate, And so even if k is varying, you are dividing by k, so the gain is R2 over R1, determined only by passive component. You can say here, this is the key to make good systems out of bad components. And that's one of the amazing properties of feedback. And there you have Bode, who was one of the contributors to theory, and there is Nyquist. And Harry Nyquist was born in Sweden. And the person who was born, he was born as a poor farmer. He wanted to become a school teacher. The situation in Sweden, the social situation was that a person with this background could never get become a school teacher. So he went to the United States, and then he went through all sorts of schools, ended up at Yale, got a PhD in physics, and then he ended up at Bell Labs. Amazing person. So now we come to the power of feedback. And when I teach control, this is one of the first things I tell them. That feedback has some amazing properties. You can make accurate systems from imprecise components, like electronic amplifiers. You can reduce effects of disturbances and component variations, like in process control. You can regulate, stabilize, and shape behavior, like you do with aircrafts. Great things. What are the drawbacks? Well, number one, you may get into instability. Whenever you close a feedback loop, things may start to oscillate. In electronics, they said that the amplifiers were singing when they were oscillating. So they were talking about the singing problem instead of the stability problem. The other thing is whenever you close a feedback loop, you're feeding sensor noise into the system. You must make sure. So we have some great positive things, but you have to watch out for instability, and we have to watch out for sensor noise. Now, that's the reason why stability theory is so important in control, because, you must know the drawbacks that you have. So then we come to the scene of 1940. What we have around 1940 is that was widespread controls in many different fields: power systems, process control, autopilot, telecommunications. And people didn't recognize that there were similarities between them. But because of the war effort, when they brought all these people together in the same room, they discovered that we have a lot of things in common. And that's why I'm saying that control is common to all engineering. So then they discovered, and they were taking, for example, the theory from telecommunications, where they had advanced relay theory, and we essentially got the body of knowledge that you can call control. So then the discipline emerged. The drivers were the war effort, and they were doing gun sight, they were doing radar, they were doing pilots, etc. The concepts were feedback and feed forward. The design tools were block diagrams and transfer functions. The simulation was analog computing. So all control labs had analog computers. Sometimes they had built them themselves. For example, here in Norway, you had one. And we were later in Sweden to build our own analog computers. And so you simulated using analog computers. You implemented the control system by analog computing. So a control engineer at the time has to be very good at analog computing, because that was the tool he used for analysis. That was also how he implemented the systems. And there was a holistic view of theory and applications. So in the same group, you had people who were solving real problems, and also people who were developing theory, because they were focused on solving real problems. So here we have the Servomechanism Theory. The theory of complex variables and Laplace transforms. We had the system concept of feedback and feed forward. And the design was frequency response, often graphical methods, analog simulation, analog implementation. And this picture here is actually the Norwegian analog computer that you had here at the institute here. This is something I got from Saab. It's a hardware in the loop simulation. So this is an aircraft, and they have the real actuators in here, and then in the computer sitting here, they simulate what's happening when you fly. So it's hardware in the loop simulation, where you take part of real hardware, and then you simulate the rest. Here's a nice picture from a German textbook, Kleines Handbuch der Regelungstechnik, by a man called Oppel. And it illustrates the block diagram idea, that you hide the internals of the system, you only look at inputs and outputs. So, computer scientists often claim that they've done many things, but we were much earlier than them to do information hiding. And then if you just make boxes in here, you have the regular block diagram. here is one of the books that came out in this area that's called Servomechanism Theory. And what's remarkable here is it was written by 3 people. One was James, was a professor of mathematics at Purdue. Then we had Nichols, and he was director of Taylor Instrument, who was an instrument company. And then Ralph Phillips, who was a first-rate mathematician. So even at the early stage, control was a mixture of physics, mathematics, and control. And I think it's interesting that in the early stages, you have all these 3 people contributing to it. And then there were consequences. As I said before, we had education. We got lots and lots of applications. People found out that feedback was very, very useful. There were special industries that were devoted to control. We also got organizations, journals, and conferences. And one of the most important one is IFAC. There was a meeting at Heidelberg. There were plans after the war to have lots of control conferences in Europe. And then the Germans took the initiative and said, we have to get organized. And they arranged a meeting in Heidelberg and said, well, we can't have this chaos. We are going to have an organization that's going to straighten this sort of thing out. And they signed a letter that they were going to found the International Federation of Automatic Control. And one of the people who signed them was Jens Glad-Balken. And you may know that you can also see him on Norwegian airplanes sitting up there. So Jens had, he was, I think, the only one from Scandinavia who participated in this conference. So it showed, that he was very early on the train of developing feedback control. There might be a professor from Sweden, but I'm not so sure of that. Then, the next phase, the golden age. What happened then? Well, that was, I mentioned before, we had the drivers. Was the space race and computer control. And also we found out that Laplace transforms and things were not enough. We had to deal with nonlinear systems and things like this. So there was drivers from applications and from mathematics. And I was lucky enough, I started to work for IBM in 1960 to put a computer on a paper mill. So I was very lucky to come in on this in the golden age phase. It was a very rapid growth of subspecialities. You got optimal control, you got stochastic control, you got system identification, you got a whole slew of things. We also got computational tools, primarily MATLAB. And there was an impressive development of theory. But you lost the holistic view. For example, if you were a professor in the United States in 1960, it was very easy to get money to do whatever you wanted. So control became highly specialized. And there were many books on, so you were losing the holistic view, and you were losing the contact with reality in many places. Theory developed, which is not naturally useful, and of course I think every field has to have a period like this. But on the other hand, there were also many silly things being done. Typically, suppose you're a professor in the United States, and then you you do your PhD, and then you get hired as a professor. And you're judged by how much you publish, how many students you get in, and how much money you can grab. Okay, what do you do then? Well, I had some problems in my thesis that I hadn't solved. So you set some students to do PhD on that. And then after 3 years, they come out in the same situation. So the things gets less and less interesting, because you have one thesis here, and then 3 years later you have some problems for that thesis, 3 years you have. So there was some not so healthy thing happening at that time. And then of course money runs out, and then people have to go out and find other ways. You get involved with industry, and then you get in contact with reality again. So I think here in Norway, you were very lucky that you had to stay away from that. On the other one, there's some great things happening. Number one, we got optimal control theory. And this was typically driven by the space race. You wanted to shoot up a satellite, and you had weak rockets. So you have to, if there were no air, you would burn everything immediately. That was the best way to get it out. But if you burn everything immediately, when you go through air, you lose. So that's an optimization problem. So Richard Bellman, he was following the ideas Hamilton, Jacobi, and Bellman, and he wrote the book on dynamic programming. In Russia, he had Pontryagin, and he was following Lagrange and Euler. And then, of course, later we got model predictive control, which is a way to implement this. But essentially, the space race gave us optimization. We also got Kalman filtering. It was recognized during the servo system time that noise is important. If you're going to track an aircraft with radar, you have to watch this out. So Wiener did this Wiener filtering theory. And then Kalman, he came up with a very efficient way to combine physics and sensors. Do you have something to discuss? Some question?
Do some logistics.
Okay, okay. And Kalman also came up with this idea that it's not written so much that a new controller structure. The controller should consist of a Kalman filter and a feedback. And see in here, you are feeding both the input and the output into the Kalman filter. This gives you a lot of lead because when you know the signal, you know what's going to happen in the future. And then you have the state space feedback here. And then you generate feed. Kalman didn't worry about this, but you generate the desired output, and then you generate the feed-forward signal sitting there. So we got a much better understanding of the role of sensors. And then also we did system identification. When I was working for Billerud, I still remember I tried to model the plant, and when we measured it didn't work. So we said we have to do experiments. And we also need to get the noise out. So what we did, we perturbed the process like this. And it's not easy to persuade a factory management that you should change things intentionally. So what they did, first they wouldn't let us try it all. Said, let's do a trial test. This often we're going to experiment. You put all your quality people on it and see if we do some damage. They didn't see a thing. And then we were allowed to do these things. And we were picking up nice models, and we could, instead of having a distribution like this, you could sharpen the variations and move much closer to the sensors. So that was an interesting exercise. We also wrote the code in Fortran to do this. Then we got adaptive control. And so the motivation was that it takes a lot of time to do system identification. Can we get a controller that does the same thing? And we did case studies. And nowadays you talk about Harris index. That's a way to measure how well you do. And why not make a controller and do it? ASEA started a project, and they came up with a controller called Novatune. The guy was running this, was one of my students. I think they moved too slowly, so he jumped off and started his own company called First Control in Västerås, who's still existing. And they actually do an adaptive controller right now doing Raspberry Pi. That's doing very well. Here is an experiment we did. You see, here is Lund, and here is Trondheim, and here is my hometown Östersund. So this is roughly the middle of Sweden. And I had some master student who was working in a mine up here, and they were doing an ore crusher. It was very difficult. We suggested they should use adaptive control. They didn't have a computer, so we were using telecommunication with homemade modems in 1975 to control an ore crusher from there. So that was a fun project. We actually had an extra telephone line for supervision in case something went wrong, you could stop the process. Here's another thing, autopilots. Near Lund is a city called Malmö. We had a large shipyard that was doing ships and autopilots. So we did a project with them to do adaptive control of ships. The main thing with ships that are the disturbance of waves, and they are changing. So you must have a controller that's estimating the effects of waves and counteracting them. And it was a fun thesis project. He simulated a Lund, then flew down to the Persian Gulf, installed the project on the boat, and then go to Cape Town to do experiments and come back. And here you see the diff. Conventional autopilot is essentially a PID controller. And here you see the heading variations. And so we were running adaptive for an hour, PID for an hour, adaptive for an hour. So this is a reasonably fair comparison. You see much less fluctuations. And also if you look at the rudder actions, they are more or less the same. There's a little bit more high frequency in this. And you got a 3% reduction in consumption. And they made a pilot called Kockums Steermaster. That's now, I googled this, it's still sold, but now sold by both Sperry Marine and Northrop Grumman aircraft. Then we come to PID controllers. And in 1970, I've been professor for 10 years. I thought I'd done everything. I graduated I think I graduated 15 PhD students. One of them actually became a professor, Lennart Jung. So I had to do something. I worked for I had to do something else. I only knew large companies. So then there was a good deal. So I worked for a very small company for half a year. And they were agents for British companies who is called Eurotherm, who did analog temperature controllers. And we've been working there for about 3 months. My man said, you should go to England and talk to the guy at Eurotherm. His name is Mike Somerville. So I went there and I was convinced that you could do something about PID controllers. And what you needed was you needed a way to tune them. You needed a way to tune the PID controllers. And then together with Tore Hägglund, who is coming here pretty soon to join me, isn't he? Huh? Sigurd?
Yeah, well, I hope so.
Yeah? So Tore is coming here. And then we came up with a very cool way to tune PID controllers. And what we do, you flip in a relay. And then you get a limit cycle oscillation. And what happens with this limit cycle oscillation? Well, here I've shown the input, which is the relay, and here's the output. And now you see the input and output are 180 degrees out of phase. So you're really measuring automatically the point where the process has 180 degree phase shift. And based on this, we could sort of say, find out controller parameters. And it put us on a journey to look into PID control, which I would never have expected before. And the journey isn't finished yet. There will be a nice dissertation here tomorrow on tuning of PID controllers. And we got a patent for this, and it's used in many, many systems. It's used by Emerson, it's used by, so here you have a box and you have a PID, and used by National Instruments. And we can also, you push a button to tune it. And then we can also generate gain schedules. So if you have a scheduling variable, then you make a little table with different quantized values of the scheduling variable. Operate in one region, push the schedule, push the tuning. Operate another one, push the tuning button. Operate a third, push the tuning button. And then you build up a gain schedule. And there are hundreds of thousands of this system out there. And they are working quite well, but there can still be improvements made on them. So, and I'll give you one example. The situation was we had been, we were working with a company that was making small DCS systems. And we had been installing, had about 20 loops. We've been installing this in a paper mill up in Sweden. And then the guys came to us and said, you know, we have this nasty process here. We have not been able to tune well. Couldn't you try to put your magic device on that? So we connected, and this. That's why we couldn't get the plots into the computer. So this is strip chart. So time goes in this direction. So this controller didn't have derivative action, had gain 8 and integration time of 2000 seconds. You see it's oscillating. At 11 o'clock, we put it into manual. And then at 2 o'clock in the afternoon, we push the tuning button. And now what's happening in here is that here we are, the tuner is actually measuring. So from here we go to it's measuring hysteresis, and then you see you get something that looks like a relay oscillation. So, you know, this is 3 o'clock. We weren't worried about this, but around, 6 o'clock, you say, well, is this really going to work? Sure enough, at 8 o'clock, it goes automatic. And look how well it's controlling. And see what's done. It reduces the gain, increases integral action, adds derivative time. So I think that's a nice real-life industrial example of automatic tuning. I should also talk about robust control. When all this mathematics came into control, you can say around 1960, started by Kalman's papers and many papers. You had, so to say, a separation of the field. You had, the old guys who knew frequency response. And they had the new guys who were working on matrices and mathematics and things like this. And the view of the new guys was something like this. You only need to have observability and controllability. And if you had this, you could control a system. And then you had the classical guys said, what about time delays and poles in the right half plane? We know that they are creating trouble for us. Where does this pop up in your theory? And the other guys go and say, oh, you guys are old-fashioned stupid, You should just learn matrices and stuff like this, and you could figure things easily. And then the guys go over. And one of the most aggressive ones was Isaac Horowitz, who said, guys, you don't know anything about control, This is the right way to do control systems. And this went on for many years at conferences. And I think we can learn a lot from this, because what they should have done, they should have sat down and say, okay, and have a gentlemanly discussion instead of becoming religious, as they did. So it took about 10 years before this was sorted out. And it was sorted out by George Sames. And then there was a famous 4-author paper, John Doyle, Kargonekar, he's at Cambridge,
Nobel.
Keith Glover, and he's a Canadian. Yeah. So they wrote a paper where they sort of, he had sort of figured it out, but these guys wrote a very, very nice paper where they were connecting the modern control theory to the robustness. And I have to tell a story about John Doyle too. At MIT, if you have state feedback, you have tremendous, so in other words, if you can measure everything, control is very easy. And you have guarantees, you have an infinite gain margin, and you have a 60-degree phase margin. So that's why they thought that everything was clear. But now if you only measure certain outputs, the story is very, very different. And at MIT, Mike Athans, who was a very dominating person, he had a research program called Stability of System Without Feedback. And John Doyle, he was a young student that came in there, and he learned a little bit. Then he went to do summer work at Honeywell, so came into contact with practice. And then he wrote a very famous paper called Stability Margins with Output Feedback. Abstract, there aren't any. And then, could the engineers please go to the storage room and pick up the Nichols chart? So he had to leave MIT for Berkeley to finish his PhD. But that's a paper I would recommend you to read. So they figured out that time delays are important limitations. Poles and zeros in the right half plane are serious limitations. And if you really like to learn about this, there's a very nice book written by Skogestad together with Postlet-White. That's a nice book which summarizes practically all of that. So that was robust control. And that's a little sketch of how things developed. And now you come to control everywhere. There are applications everywhere in control. And I think that's why all engineers should learn it. So, you have the power systems, you have process control, you have aerospace, you have automotive, you have buildings, you have robotics, you have computer systems, you have global enterprise control, you have advertisement, you have mobile phones, you have arts and games, you have physics and biology. So control is spreading everywhere. And I'll give you some examples of this. Here is from a paper mill where it's work done by ABB. They have modeled the whole plant, something like lots of production units, buffer tank streams, and measured variables. So what they do is that they do state estimation, they optimize, and then they simulate. And many of these are run by teams. So when they come to this stage, they simulated. They typically have production meeting once a week. So then the people meet once a week and tell, this is the situation. We know that on Tuesday we are going to switch down this one, and that's why we're changing. And we know that on Friday they are a little short on that team, so therefore we have to run it a little bit more carefully. So they are doing optimization, but they do something automatically, but many things are adjusted depending on the situation, what it looks like. So, and then you can look at higher levels. There are efforts, for example, to merge control with a business system. So down here you have the operational process control, and then you have the manufacturing systems, and then you have the strategic enterprise control hanging further up. Here's an example from General Electric. They do trip optimizable trains. You're going to go send trains with loads from one place to another one. You would like to arrive in time, but you don't want to do too much energy, so you don't want to brake too much. So they've done a nice system to do that. And of course, automotive. That's a tremendous area for many reasons. Number one, you make so many cars. And so if you make so many cars, you have a lot of influence on the market. So for example, we got the microcontroller thanks to the automotive industry. They figured out that they needed to have feedback in cars to satisfy the California emission requirements. So they needed to have feedback, they needed to have a computer. And they needed to have a cheap computer which also had A to D and D to A. So they forced essentially Motorola and Intel to make the microcontroller. And once you got the microcontroller, of course, you can use it for many, many different fields. And then nowadays you have cruise control, adaptive cruise control, collision avoidance, traction control, lane guidance assistance, and platooning. And of course you have all the thing about autonomous cars that's shaping up right now. You do automatic powertrain control. I'm going to skip that. I talk about mobile telephones. I call that billions of systems. So there are about 10 control loops in the mobile telephone you're carrying around. And they do frequency control, and they do, very important in mobile telephones is to use as little power as possible. So that's one of the major reasons. Another thing that's coming up is control of computer systems. When you build up server halls, you have a number of problems. You have incoming computing demands that you have to distribute among different computers. Also, you would like to keep the energy low because they are consuming a lot of energy. So you don't want to start computers that you don't have to need. And then, when jobs are coming in, maybe you can load a little bit more on the computers, and maybe you have to start up new computers, and you have to start up new computers in time. So it's a very nice collection of control problems, both to control the energy distribution itself. You can actually slow down a computer by lowering the voltages. Then you use less energy and you don't process quite as fast. So there are very interesting control problems in that area, which is bringing us close to computer science. And the same with energy management in data center. Here's a more unusual one. I had a student both in Lund and in Santa Barbara called Niklas Karlsson. He now works for a company that does online advertisement. So what you do, you plan a campaign. And the nice thing about the internet is that you can measure the effect of advertisement campaign. You see, for example, how many requests you see how much people are selling. So they are doing decentralized control of advertisement, which is a very unusual application of control. So it just shows the diversity where you stand. I should also mention art and games. There's a very creative researcher at ETH called Raphael Dandria. And he has done many things. How am I doing with time?
I think it's okay.
It's okay, okay. This chair is at an art museum in Toronto. And what happens with this, I'm not allowed to show the video for it, so you have to go to RAF and look it up. 2 years ago, I couldn't show the video. So what's happening? This chair is falling apart. The legs are spreading apart and sitting there. And then the seat walks around, gathers the legs, and puts it together, and then it raises up again. And they start all over. So I would really recommend you to do this. He has also done participated in RoboCups, which has won. And also, there is a company called Kiva Systems, which is now bought by, was started by RAF together with some economists. And what they were doing, they were handling things for Amazon. In the warehouse in Amazon, there are people sitting there and filling up the orders. So they made a system with small little movable robots, very cheap equipment that's moving around and gathering the stuff, and then there's a person sitting centrally. And this is now bought by Amazon, who's selling them to other companies of a similar type. So you should really Google him to see a little bit of that. Then we come to physics. And the 1912 Nobel Prize in Physics was given to control. And it was given to a man called, the invention was, for lighthouses, you have a switch that switches on the lighthouses when it gets dark and switches them off when it gets light. And the idea is that you have 3 pieces of metal, 2 are dark and 1 is reflecting light. So that was the whole idea. And number 2, he had a system for distributing gas into that. His name is Dahlén, and he started the AGA company. And he got this Nobel Prize. So I wrote it here in Swedish. For his invention of self-acting regulators in combination with gas accumulation to use for lighthouses. And the candidates at the time were not bad, you know, Cammell-Eons, Max Planck, Albert Einstein, Walter Nernst, these were all proposed as candidates. And then the physics committee unanimously, they selected Cammell-Eons. But then there was one member of the academy who said, you know, this is all wrong. We should read Nobel's testament. And what Dahlén has done is much more useful for society. So therefore, I suggest we should give it to Dahlén. And it's called, nowadays the papers are published. Well, you know, it takes a while because much in the Nobel are secret. So Dahlén won by 37 to 28. So that was the first time that control really made it into the Nobel committee. And it was called a scandal in the Nobel committee and things like this. So in physics then, here was his Nobel Prize. There was another one. It was a Dutch engineer called Simon van der Meer in '84, quite a bit later. And he got it for, you know, in this accelerator you're circulating particles. And you're trying to control the particles as well. And he called it stochastic cooling. So it was a control scheme for doing this. Then in quantum and molecular systems, there's quite a lot of interest in control. Here's a thing I would mention. You know, in hydromechanics, there's always been a question, how does turbulence come around? And the traditional way to, you're looking at the Navier-Stokes equations, you know, messy partial differential equations. And people thought that if you linearize the Navier-Stokes equations, they will become unstable when the Reynolds number goes up. That doesn't happen. So they were a little bit puzzled about this. And then there were some control engineers from Santa Barbara, incidentally, who looked at this. They look at the flow, and they look at perturbations in the edges to see how this flow propagates into the flow itself. And that you can characterize by an operator. And this operator has a gain. And then they figured out how does the gain depend on the Reynolds number. And they got very nice agreement with experiments. So they were able to, you know, to explain a very difficult hydromechanical phenomena as essentially has to do with the gain of a linear operator. And it was accepted very quickly by the experimental community. But they had great difficulty to get it published in the traditional journals, you know, because people didn't think, you know, here are some outsider coming trying to tell us something. Then we have something else. We have instruments. You have adaptive optics, where essentially you're looking at a star far away, and then you're using feedback to try to reduce the effect of the atmosphere, because when the light goes through the atmosphere, you get distortions. And then you are trying to use a control system to get rid of that. And that has been a very successful operation. And then you can go to the nanoscale and look at the atomic force microscope, where you're trying to measure atomic structures. You know, what you have here is that you have a very narrow tip here that's sitting on an elastic beam, and here you have a piezoelectric device that pushes it up and down. And then you put light on it and you scan here. And then you're moving this over the surface, and then you are regulating this piezo sitting here so that the voltage between this one and this one is roughly the same. You can really map things on the nanoscale. And then we have biology. This is an interesting book written for children. And it's written by two biologists. It's called The Way Life Works. And it has 7 chapters. And one of them is about feedback, which is interesting. So out of 7 chapters, 1 chapter is devoted to feedback. And here's what they say. Feedback is a central feature of life. Process of feedback governs how we grow, respond to stress and challenge, and regulate factors such as body temperature, blood pressure, cholesterol level. The mechanism operates at every level, from the interaction of organisms, proteins in cell, to the interaction of complex ecologies. This was written in '98. And now you know there's something called systems biology, where, for example, one of our say a small number of control engineers are moving into that field. And at Harvard, for example, they have a big department on systems biology. So that's an interesting field to work with. I must also mention the birds. And you may remember I said that the Wright brothers were able to fly because they made an unstable aeroplane. Well, nature discovered this a long time ago. So this is a paper written by John Maynard Smith, who was a biologist, say the importance of the nervous system in the evolution of animal flight, published 1952. And you can read yourself what he's saying. He says that there was a tremendous advantage. The early birds were stable, you know, they fly like an arrow. And they were sort of dinosaurs. And then as birds developed, they discovered there was a tremendous advantage to have maneuverability. And the best way to get maneuverability is that the bird is unstable. And then it gets stability by having a nervous system. So as the nervous system developed, the birds actually became stable. And so you had actuation, you know, in the wings. And then you had sensors. And you could actually maneuver. So I think that's interesting that nature discovered this a long time ago. And then, of course, all the modern fighter airplanes, they are unstable because of this. Then we move into another area, namely economics. And here is John Maynard Keynes. You know, he wrote one of the early famous books on economics. So he's an econometrician. And here's Krugman. And he got, you know, there is no Nobel Prize in economics. Because when the Swedish State Bank celebrated the celebration, they donated money to the Nobel Committee to give a prize in economics. But it's not a Nobel Prize. It's the Swedish Bank's prize in economics to the honor of Alfred Nobel. But the economists were smart. Nobody can say this, so they call it the Nobel Prize in economics. But it's not a Nobel Prize. There's always fight about this in the academy, because the physicist says, you know, this is absolutely ridiculous. You know, how can you give a prize to that? So that's interesting. But anyway, here's what Krugman says. We have magneto trouble, he said. At the start of the Depression, most of the economic engine was in good shape, but the crucial component, the financial system, wasn't working. He also said, we have involved ourselves in a colossal muddle, having blundered in the control of a delicate machine, the working of which we do not understand. Both statements are as true now as they were then. He said this, you know, after the recent economic crisis. So essentially what he's saying that, here's a noted economist who's saying, you know, we don't understand economics. Okay, that was a little bit about control everywhere. So now let's move to challenges. I think we have some interesting times ahead of us. Oh boy, has somebody some urgent thing to do? You should go. Okay. So number one, we are getting complex network systems. We have what I call sensor and actuator rich system. You know, in control, if you have about 100 sensor, 100, we can solve this. But if you have a camera with the pictures, that's about 1 million sensors. And we can't have the same architecture to deal with that. You have to do a lot of local computation. Another thing is to do safe design of embedded systems. Now we are going to have autonomous cars. And then we must, of course, guarantee that they are operating in a safe way. And we are certainly not there yet. We have autonomy, we have adaptation, learning, reasoning, cognition, and we have things happening in biology. So there are many, many things for us to do here in the future. We have, for example, autonomous flight. Here's a slide from the US Air Force, which says that they are really needing, and in the 40s, they are needing autonomy in a large scale. And of course, you have the cars. You've all read about, you know, the competition for the cars. You're all seeing about more and more autonomy creeping into the cars. Here is a slide from the Silicon Valley. Here is a collection of all the companies around Silicon Valley who are working on autonomous cars. Nice collection. So I think we are entering a third phase. The drivers are complex network systems, physics, and biology. We need to have autonomy, we need to have adaptation, which we know a little bit about, but we need to have learning and cognition, which we know much less about. We have sensor and actuator-rich systems, and we should have provable design and reconfiguration. You know, when you start to get your autonomous car, you drive it in, they're going to fix it. We must make sure when they fix it that it's working properly. And we are not able to do this yet. And I think we can recover the holistic view. So here's what they say in the National Academy of Engineering in the US, in the books Engineering 2020. They say that in the past, increase in knowledge has spawned new microdisciplines within engineering. However, contemporary challenges from biomedical devices to complex manufacturing system to a large extent is a system of network increasingly requires a systems perspective. And that's something we in Control are getting used to provide the system perspective, because we were, after all, the first systems field. So here's my little picture of this. Here to the right we have the real world. Here we have engineering, biology, and economy. And here to the left we have mathematics. And then in the middle we have computing, control, and communication. So what we have to do now is no single person can cover everything. So we must have a person who is, for example, very good in communications. But he must know enough about these neighboring things in here to contribute. And that poses, a great educational challenge. I'll give you one example of this. In the automotive industry, there's something called the CAN bus, which is used for communication. They're also more and more using it for control. It's a very nice little protocol, nice, requires little chip area. And if the guy who has designed this had taken a good basic course in control, he would know time delays are bad. Variable time delays are really bad. It doesn't take much of a control to do. But had he taken such a course, he would never have designed this thing, because the CAN bus has variable time delays, which is creating a mess when you're trying to control it. It's all right to raise the windows, but try to do a control system over it, you're in real trouble. So so what we have to do, we have to educate people who are very good in some areas. But if they work in this field, they must know the neighboring areas enough so that they can ably communicate with the people up there. And it also means that in systems, you're not just relying on yourself, you have to collaborate. So it becomes very important to have communication abilities. Not just sit and work yourself, you have to work in teams in order to solve this. So that's a challenge for us in education. Talking about one specific barrier, the barrier between computer science and control. So in control we deal with feedback, stability, partial differential equation, moderate complexity. In computing they work with logic, languages, finite state machines, formal methods, abstraction, and architecture. So what you typically do, you design a control system here in Simulink, you throw it over the border and then have the computer scientists implemented this. This is not the right way. Look to what happened in the early control when we had analog computing. Control engineers knew about analog computing quite well. So what we need to do, we need to have control engineers who know enough about computing to be able to implement things. At the same time, we must have computer scientists who know about control so that they can understand the interactions that's happening in here. I should mention about computing too. So I start here with a quote from Vannevar Bush. He was professor at MIT, was working in power system. And he said that engineering can progress no faster than the mathematical analysis on which it's based. Formal mathematics, frequency inadequate for numerous problems. A mechanical solution offers the most problems. And then he built the mechanical analog differential analyzer that could solve 6 differential equations. And you could program it with a wrench, okay? When I worked with IBM Research, I was in the math department in Yorktown Heights, which was headed by Hermann Goldstein. And Hermann Goldstein built the first computer with John van Neumann. And he was head of the math department. And he said like this: when things change by 2 orders of magnitude, it is evolution. Revolution, not evolution. So when you can do things 100 times faster, it's not just evolution, it's something else. And you combine this with Moore's law, you get a revolution every 10 years. So what's happening, since about 1960, 1970, is that computers have developed tremendously. But it hasn't translated into engineering productivity. We are not 10 times more efficient by year. And of course the reason is that we have not been able to exploit this potential. So there's a great potential in trying to exploit computation in all sorts of ways. Okay? Then we come to the next barrier, the physics barrier. So here we have control, and here we have physics. So you have, here we work with block diagrams, order differential. Here we talk about mass, energy, and momentum. And I would say block diagrams are very useful, but they are not very useful in capturing physics. And the reason for this is that information transfer in block diagrams is unidirectional. And in physics, interaction is always bidirectional. So we should not try to convert everything to block diagrams. And here's what the National Academy of Engineering says. They says that in here about modeling and simulation, that there will be a growth in areas of simulation and modeling around creation of new engineering structures. Computer-based design-build engineering will become the norm for most product designs, accelerating the creation of complex structure for which multiple subsystems combine to form a final product. I know a very nice example of this. How many of you have heard the word Modelica? Can you raise your hand? Fantastic. Modelica started and learned by one of my PhD students, Hilding Enquist, in 1978. He was much too early because the only object-oriented language he can use was Simula, a genuine Norwegian product that was not widely used in industry. So it took a while for it to emerge. We have two companies in Lund right now who are working very hard on Modelica. One is a company called Modelon, and we call them the thesis factory because we are using so many master theses. And they did a very nice things with the automotive climate control industry. They asked, the major German manufacturers who are making cars and the suppliers for climate control systems to get together. And the climate control system now delivers a piece of hardware and a validated Modelica model. So what you do then at the car company is that you combine the system, and then you run the European cycle, you analyze what's the climate comfort and what is the energy consumption, and then they make their choices of that. And in order to do this, they are using encryptation to protect IP, because the component manufacturers were very afraid if we give you a model, we are giving away IP. But by doing encryptation, they could get around this. So I think that's a nice example of modeling, that you are combining modeling this. And then we come to educational changes. To educate the future engineers. And I think here at the Institute of Cybernetics in Trondheim, you're really blessed, everybody here apparently takes control, which I think is fantastic. So we have to educate the future engineers, and we have to educate physicists and biologists. And I say there's a dilemma of emerging fields. Because when the field's emerging, it's not clear what's important, what is not important, and things are moving around like this. So what we have to do is that we have to spend effort to filter what are really fundamentals. And we should also exploit computing. So if you're going to give a basic course in control, and you know that this is the only course the computer scientists and biologists are taking, what things should be in that course? And that's not obvious. I personally think, for example, root locus should not be part of that. But it's not obvious, so one should really argue about this. What should be in the basic course? And we need to have deep knowledge in specific areas. We have to have broad knowledge in neighboring fields. And this means that the neighboring fields, they also have to give, one good course that gives you a very good perspective what the field is, or maybe 2 or 3 or something like this. So this is not just for control, it's essentially for the whole community. But I think the control engineers are the only systems people, they should be driving this. And I said before that you have to have broad knowledge, and also you have to have ability to communicate and work in teams. So we're now coming to the end. So I gave an introduction, a brief history, told about control everywhere. I talked about challenges and conclusions. So what are the conclusions? I think control is still a very vital field. So if you decide to work in control, you really made the great choice. Networked embedded systems is one new emerging area. Autonomy and safety is another one. We have to deal with the educational challenge, so we should continue to take care of the foundations and then to develop the holistic view. So what's the final word? Here comes the final word. For those of you who only know English, it says, control, control. You must learn control. Thank you.